Hello and welcome to Biorules video lessons. Now that you know about resting potential and actual potential, the ones that you have here just in front of you, let's make a quick revision so we can talk about how the signal that happens in one place, by an actual potential, is transmitted along an axon, which is transmitted along a nerve cell and actually all over your nervous system. So if you take a look here on this square, showing the resting potential, the resting state, we are going to see that you have a lot of sodiums outside, some potassium inside, and the channels are closed. So the sodium-potassium pump is pumping, and keeping lots of sodium inside, lots of potassium inside, and this relatively negative charge of minus 70. When the threshold is reached, like over here, the threshold is reached, we have a depolarization. Sodium channels, they are sensitive to voltage and they open at minus 55. At that moment, sodium enters and flood in the inner side of the axon. The inner side of the axon being flooded, you have a depolarization. Yay, like that. Lots of sodium inside. At this very moment, we had the depolarization with the sodium entering over there. The sodium potassium, the sodium channels, they close, so sodium starts bouncing, and actually you have a fairly equal amount of sodium potassium from between both sides. But the potassium channels now they open, and the potassium now are going to be leaving, and when they leave, the inner part becomes less negative, and you have a repolarization of the event. Through all this step here, we had a signal. At this very moment over here, the sodium channels over this part over there, the sodium channels, they were closed. The potassium channels are causing the repolarization. And now, at this very moment, on the bottom here, the sodium is more or less balanced between both sides, so there's no potential concentration of sodium in both sides. The same for potassium. And then the channels close, and the sodium potassium keeps pumping, and you reach the resting potential back again to be able to have another place. So all this here happened in one spot of the axon. So what? How is this going to be contributing for a signal to be transmitted along an axon? So it's going to be like this. At this very moment over here, we are having, you see here in the bottom, we have a depolarization. Sodium is going in and is making the inside become relatively positive, something around plus 30, plus 40. And actually, at this point over here, the sodium has gone in, but part of the sodium ends up getting to the surrounding adjacent area. So a little bit of positives that are causing the depolarization in here end up getting into this point, actually over there. And when a little bit of the sodium gets over there, we have from minus 70 going to minus 55 and reaching the threshold. So at this moment, the sodium channels are going to be opening, the sodium is going to be flooding in, the depolarization is going to be happening, and at the same time, in the back part here, we are having the repolarization going down in there. So when you have that depolarization in this part over here, a little bit of the sodium moves, and we reach the threshold, minus 55. And at that moment, we have a depolarization with sodium getting in again, and this part over there is having the repolarization. And then we have the repolarization here, while we're having a depolarization over there. So in the end, what's happening over here is that, let me clean this slate here for you to see how it goes. We have a depolarization over there that causes a depolarization there, that causes an extra potential over there, that causes an extra potential over there. So one extra potential causes an X, that causes an X, that causes an X, and go on and on and on. This is the idea of the transmitting the impulse by actual potentials. We have the same stuff happening here. We have an actual potential happening in this place. We have a depolarization, which is going to happen because sodium is entering, and a little bit of the sodium is going to end up causing the threshold to be reached here, and then you have a depolarization there. In the meanwhile, repolarization is happening on the one that has just passed, and then that depolarization causes another repolarization there, and so on. This is the idea. We have here the transmission represent this here as the entire step where you have resting potential over here, and then because of a signal before this region, this part here became minus 55, opening the sodium channels, depolarization, and when it opens the sodium channels, it causes another part to be opening and having an actual potential there as well. And here comes a very important part. At this moment over here, where you have the repolarization, the potassium channels are open, but the sodium channels are closed. So at this moment, even if we go through the minus 55 here, the sodium channels are closed, and you're not going to have a new actual potential, even because we are in a moment here that sodium is evenly distributed between both sides, so there's nothing to move by diffusion this sodium to the other side. So we have here a certain while that goes from here to here that you're going to be calling the refractory period, a period that whatever stimulus is given, it refracts, it doesn't get stimulated again. And this is going to be very important to make the signal to travel only in one direction. Let me show you here once more. We have here a depolarization is happening on that part, which is making no sodium getting in, and a little bit of sodium gets there, which is going to be causing at this region here in the bottom, reaching the threshold and depolarization. This depolarization is making sodium to enter to both sides, but this area over there actually is having a repolarization and refractory period. So it's not going to be stimulated again. This here is not going to be happening. So the stimulus is only going in that direction. A little bit of sodium comes over here, triggers a new actual potential while you have a repolarization over there, and then this one is going to trigger another one over there while this one goes and on and on and on. This is how it is transmitted. So the idea is that when you have an actual potential happening here, even though sodium moves and spreads from that point to both sides, it's going to be triggering, reaching the threshold over here and triggering a new actual potential over there, but it's not going to be triggering an actual potential here because this part actually is coming from an actual potential, is going to repolarize and it's going down. So this part here is not possible to sensibilize it, so there's no way that you're going to have another actual potential where you just had an actual potential. You need a few milliseconds for a new actual potential to go on. And in the meanwhile, this here went up, so this here is coming down. So there's no way that it's going to be starting just back here, but it's going to be starting another one over there. And then this goes down, and then this goes up, and it goes on and on and on. This is the idea of the stimulus. And the stimulus going in only one direction. If I come here, if you have a stimulus happening here, you have reached threshold, depolarization. This is going to be causing a depolarization in another part. And that polarization over there could make this area here to reach a threshold, but it's not, because actually at this moment we are having this, we are having the repolarization. So nothing happens. And this takes a few milliseconds. We have here about 1.5 to about 4 milliseconds all this time here. So you have about 2 milliseconds that the area of the nerve cell cannot be stimulated again. So the signal travels only in one direction, like I just showed you here. Another thing that is interesting for us to understand is about the speed of traveling, and this will have to do with this actual potential traveling, but also to do with the myelin sheath. The myelin sheath is this Schwann cells over here. We have the Schwann cells that surround the axon and actually insulates electrically the axon from the surrounding, apart from the nodes of Ranvier. This here is a node of Ranvier. We have here nodes of Ranvier, and in the nodes of Ranvier, the axon membrane is exposed. And in those places, we are going to be having, so if you have an actual potential going on here in the head of the nerve cell, enough sodium will travel through here to make this reach the threshold, triggering an actual potential, while this one is repolarizing over there. And then enough is going to be traveling here to trigger another actual potential, while this here is repolarizing. And then this will travel, so this trigger an potential while this one goes down. And so this keeps going until you reach the end when you have an actual potential there, and this actual potential is going to be making this guy here to transmit the signal. So this is how we travel. And this that I just showed you, where the impulses are jumping, this here is actually jump, 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 jump. We have signals like that actually. There, 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 and there. It's called saltatory stimulus, and this is going to be making the stimulus to be much faster and much more efficient. You only need one actual potential here. You don't need many actual potentials in the middle. You just need one there to trigger one here, to trigger another one there, another one there, another one there, and therefore another one there in the end. The myelin shaft, the Schwann cells, they have exactly the size to have one actual potential just causing enough sodium to getting in to make the next node of Ranvier to reach the threshold and starting a new actual potential. And then this here will make enough to go there to cause another one there, and then this will make another one, and then this will make another one, and then this will make another one, and then you reach to the end where this guy is going to be working. This is how the myelin shaft works. This here is the idea. One actual potential here, cause another one there, 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 there, and you got to the end. So it's much faster. If we had to go one by one like this, it would be much slower and much more complicated, sodium, potassium mixing region that didn't happen. So a myelinated axon is going to be much faster in this because it transmits the impulse much, 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 much faster. Okay? Here, how the myelin shaft works, we have in this diagram a Schwann cell, which is a cell that rolls around and insulates. So you cannot have any transit happening in here. We actually have a transit, an actual potential happening there that will cause an actual potential there because enough sodium will travel through here. So we have a saltatory conduction or saltatory impulse. So the impulse goes faster. This is how the myelin shaft works. Okay? I hope you had fun. Try to do this little quiz so to check if you got enough information about this, and let's have a discussion about this topic in class. See you there in class. Bye-bye.